Welcome to Tech Lab by Sid. In this video, we are going to discuss about synchronization in computer science. What is synchronization? Synchronization is the coordination of multiple tasks or processes to ensure they operate in a predictable and controlled manner. In computer science, it specifically involves managing access to shared resources between concurrent processes or threads to prevent conflicts. Why is synchronization important? Synchronization is crucial for ensuring correct execution when multiple tasks run concurrently. Without it, tasks may interfere with one another, leading to data corruption or inconsistent results. By properly synchronizing, we can ensure that processes do not conflict, maintaining system integrity and reliability. Synchronization is essential in computer science to coordinate multiple tasks or processes, ensuring they operate in a controlled and predictable manner. It primarily manages access to shared resources between concurrent threads or processes to prevent conflicts. For example, in multithreading, synchronization ensures that when multiple threads access shared data, only one thread can do so at a time, preventing race conditions. In distributed systems, it ensures that different computers or servers coordinate their actions to avoid inconsistencies when modifying shared data. Synchronization is used in various scenarios, such as managing a printer queue, where it ensures only one user can print at a time, or in banking applications, where it prevents transaction interference between users. Similarly, in distributed databases, synchronization ensures data consistency across different servers. Let's see the synchronous and asynchronous operation. In synchronous operations, tasks are executed one after another, with each task waiting for the previous one to finish before starting. This creates a sequential execution flow, where no task can begin until the previous one is completed. For example, in a single-threaded application that processes files, each file must finish processing before the next one can start. A real-world analogy is a person cooking dinner. They can't start cooking the next dish until the current one is done. This demonstrates how synchronous tasks follow a strict order, ensuring one step completes before moving to the next. Asynchronous operations allow tasks to be initiated and run independently, enabling parallel execution without waiting for the previous task to finish. For example, in a program handling multiple network requests, each request can be sent simultaneously without waiting for the previous one to complete. This approach maximizes efficiency by allowing multiple tasks to progress concurrently. A real-world analogy would be a team working on different tasks at the same time. Each team member doesn't need to wait for others to finish their work before starting their own. This is how asynchronous operations optimize task execution in systems. The key differences between synchronous and asynchronous execution lie in how tasks are performed and their impact on performance. In terms of execution flow, synchronous operations run tasks in sequence, meaning each task waits for the previous one to finish before starting. In contrast, asynchronous operations allow tasks to execute concurrently, without blocking each other, enabling multiple tasks to progress at the same time. From a performance perspective, synchronous execution can be slower for tasks that can be performed independently, as it requires each task to wait for the previous one to complete. Asynchronous execution, on the other hand, is more efficient for IO-bound tasks, such as reading files or making network requests, as these tasks can run concurrently without causing delays. In terms of use cases, synchronous operations are ideal when tasks must occur in a specific order, like in banking transactions, where consistency and sequencing are crucial. Asynchronous operations excel in scenarios that involve non-blocking tasks, such as handling user input or performing web scraping, where the program can continue executing while waiting for tasks to complete. Let's discuss synchronization in multithreading. What is multithreading? Multithreading is the capability of a CPU or a single core to execute multiple threads concurrently within a single process. A thread is the smallest unit of execution in a program, allowing tasks to be divided into smaller, manageable parts. Parallelism in multithreading. With multiple threads, different tasks can be executed simultaneously, leading to improved performance and efficiency by fully utilizing system resources. Benefits. Multithreading enhances performance by breaking tasks into smaller threads that can be processed concurrently. It also improves responsiveness, ensuring that a program remains interactive, as user inputs can be processed while background tasks continue running. Multithreading can lead to several challenges, with race conditions and deadlocks being two common issues. Race conditions occur when multiple threads attempt to access and modify shared data simultaneously, causing unpredictable results or errors. For example, if two threads try to update a bank account balance at the same time without proper synchronization, one thread may overwrite the other, leading to incorrect balance values. Deadlock happens when two or more threads are each waiting for the other to release a resource, causing them to become stuck. For instance, if thread 1 locks resource A and waits for resource B, while thread 2 locks resource B and waits for resource A, neither thread can proceed, resulting in a deadlock. Techniques for synchronization in multithreading. Locks or mutexes ensure that only one thread can access a critical section of code or a shared resource at a time, preventing race conditions and ensuring data consistency. For example, a thread locks a shared resource, such as a database, before accessing it and releases the lock once done, allowing the next thread to access the resource safely. Semaphores control access to shared resources by maintaining a counter that limits how many threads can access the resource simultaneously. For example, a semaphore may allow only 3 threads to access a resource at once. If more threads attempt to access it, they must wait until a spot becomes available. Monitors are high-level synchronization mechanisms that combine locks and condition variables to manage access to shared resources. They ensure that only one thread can execute within a critical section at a time, while also providing a way to signal other threads to wait or proceed based on certain conditions. For example, in a shared queue scenario, a monitor can be used to ensure that only one thread accesses the queue at a time. One thread may add data to the queue, while another thread removes data, with access controlled to avoid conflicts. Condition variables allow threads to wait for specific conditions to be met before continuing execution. A thread can signal another thread to wake up and proceed once the condition becomes true. For instance, in the producer-consumer problem, a consumer thread might use a condition variable to wait for the producer thread to add items to a shared buffer before proceeding with its task. Let's discuss synchronization in distributed system. A distributed system is a network of independent machines, or nodes, that work together to perform common tasks. These systems coordinate and share resources, but each machine operates independently. The key characteristics of a distributed system include multiple machines connected over a network and the need for coordination between them to ensure tasks are completed correctly. Examples of distributed systems are everywhere. Distributed databases, like Google Spanner and Amazon DynamoDB, store data across multiple nodes but allow access as a single entity. Cloud services like AWS, Google Cloud, and Azure distribute resources across data centers worldwide, offering scalability and reliability. Large-scale web applications, such as e-commerce websites and streaming platforms, also rely on distributed systems to handle millions of users and ensure smooth performance. Challenges in synchronization for distributed systems. Clock synchronization. In a distributed system, each machine has its own internal clock, which may not be perfectly synchronized with the others. This can lead to several challenges. Network latency, the delay in message transmission between machines, can cause clocks to fall out of sync. Additionally, clock drift can occur when clocks on different machines tick at slightly different rates, resulting in discrepancies over time. The impact of unsynchronized clocks is significant. Events across machines might appear to occur in the wrong order, leading to inconsistent data updates or conflicting operations. This can cause problems like conflicting transactions in a distributed database, where the timing of events is crucial. Next is consistency. Consistency ensures that all machines in a distributed system have a uniform view of shared data. However, this presents its own challenges. Concurrency issues arise when multiple machines try to update the same data at the same time, which can lead to conflicts. Furthermore, maintaining data integrity is vital, ensuring that all nodes have the same data at any given time, even in the face of machine failures or temporary disconnections. Without proper synchronization, different machines may have inconsistent data, undermining the system's reliability and functionality. Techniques for synchronization in distributed systems. Lamport timestamps. Lamport timestamps are a method used to order events in a distributed system without requiring synchronized clocks. Each event is assigned a unique timestamp that reflects the order in which events occurred. Each machine in the system maintains a logical clock. When a machine sends a message, it includes the timestamp, and when another machine receives the message, it adjusts its logical clock if needed. This ensures the system can determine the correct order of events. Lamport timestamps are particularly useful in scenarios where it's essential to know which event occurred first, such as in distributed databases for transaction ordering. Vector clocks. Vector clocks offer a more complex approach to track causality, or the relationship between events, in a distributed system. Each machine keeps a vector of timestamps, where each element corresponds to the logical clock of a different machine in the system. When a machine sends a message, it includes its vector clock, and the receiving machine updates its own vector clock accordingly. This method captures causal relationships, allowing the system to understand if one event happened because of another. Vector clocks are especially valuable in situations that require not only knowing the order of events but also understanding their causal relationships, such as in version control systems or maintaining causal consistency in distributed databases. Deadlock and its prevention. What is deadlock? Deadlock occurs when two or more processes are unable to proceed because each one is waiting for the other to release a resource, creating a situation where no progress can be made. The system essentially comes to a standstill, as all the processes involved are stuck, unable to move forward. Conditions for deadlock to occur. For deadlock to happen, 4 conditions must be met simultaneously. First, mutual exclusion means at least one resource must be held in a non-shareable mode, so only one process can use it at a time. Second, hold and wait happens when a process is holding a resource and waiting to acquire additional resources held by other processes. The third condition is no preemption, where resources cannot be forcibly taken away from a process once allocated. Finally, circular wait occurs when a set of processes are waiting for resources held by the next process in a circular chain, creating a deadlock loop. How to prevent deadlock? To prevent deadlock, we must avoid one of these 4 conditions from occurring. One way to do this is by avoiding circular wait. This can be achieved by ensuring that resources are requested in a specific order. For example, if process A holds resource 1, it must request resource 2 before resource 3, breaking any potential circular waiting. Another approach is preemption of resources, where the system can take resources away from one process and allocate them to another, allowing the waiting process to continue. For instance, if a process is holding resource A and waiting for resource B, the system might preemptively take resource A and allocate it to another process to avoid a deadlock. Finally, a resource allocation strategy can help prevent hold and wait. This strategy ensures that processes either request all required resources at once or release any held resources if they cannot obtain all the resources they need. Deadlock detection. In cases where deadlock prevention is not possible, deadlock detection comes into play. This involves periodically checking the system for deadlocks and identifying the processes involved. One common algorithm for detecting deadlock is the wait for graph, where processes are represented by nodes and edges show which processes are waiting for resources. If a cycle is detected in the graph, it indicates a deadlock situation. Deadlock recovery. Once a deadlock is detected, the system must take action to break the deadlock and resume normal operations. One method is process termination, where one or more processes involved in the deadlock are terminated to break the circular wait. This could involve either aborting all the processes involved in the deadlock or aborting a specific process and rolling back its actions to release resources. Another method is resource preemption, where resources are preempted from deadlocked processes and the processes are rolled back to a safe state, allowing them to restart and eventually complete without encountering deadlock. This way, the system can recover from a deadlock situation and ensure that processes continue running smoothly. Best practices for synchronization. Keep critical sections small. Critical sections are portions of code where shared resources are accessed and need to be protected by synchronization mechanisms, such as locks. To improve performance and reduce the chances of contention, it's essential to minimize the size of critical sections. By keeping synchronized blocks as small as possible, you reduce the time a lock is held, which minimizes the waiting time for other threads and enhances system throughput. Large critical sections, on the other hand, can cause threads to wait longer for access to the lock, leading to performance bottlenecks. The key here is to focus on protecting only the critical resource access and avoid adding unnecessary code inside synchronized blocks. Use higher-level concurrency utilities. Instead of manually managing low-level synchronization tools like basic locks and semaphores, consider using higher-level concurrency utilities that abstract away the complexity and improve efficiency. For instance, thread pools can be used to reuse existing threads, reducing the overhead of creating and destroying threads. Also, synchronized collections such as Java's concurrent hashmap or thread-safe data structures in other languages can handle synchronization internally, making it easier to work with shared data. By using these higher-level utilities, you can focus on the logic of your application while the concurrency framework efficiently manages synchronization behind the scenes. Avoid over-synchronization. While synchronization is crucial for preventing race conditions and ensuring data consistency, Over-synchronization can cause unnecessary performance overhead. When too much synchronization is used, it can lead to performance bottlenecks as threads spend too much time waiting for locks. Additionally, it increases the risk of deadlocks, where threads are blocked, waiting for each other to release resources. To avoid these issues, synchronize only when necessary. Focus on the most critical sections of your code where shared resources are accessed or modified, and avoid locking sections of code that do not require synchronization. Test and benchmark. Testing for concurrency issues is essential in multithreaded applications, as problems like race conditions, deadlocks, and performance issues can be difficult to detect during normal execution. To ensure your system runs smoothly, focus on testing key areas, race conditions, where multiple threads accessing shared data might lead to inconsistent results, deadlocks, where threads are stuck waiting for each other, and performance, by benchmarking to identify any synchronization bottlenecks. Best practices include automated testing using tools like stress testing, unit tests, and static analysis to catch race conditions and deadlocks early. Also, regularly benchmark the application under load to detect performance issues and ensure the system scales efficiently as traffic increases. In conclusion, synchronization is essential for ensuring the correct execution of programs in environments where multiple tasks, threads, or processes interact. It helps prevent issues like race conditions and deadlocks, ensuring shared resources are accessed safely and consistently. Techniques such as locks, semaphores, monitors, and condition variables are fundamental in managing concurrency. Understanding the difference between synchronous and asynchronous operations is crucial. While synchronous tasks execute sequentially, asynchronous tasks can run independently, boosting performance, especially for IO-bound operations. In multithreading, synchronization ensures threads don't interfere with each other, and in distributed systems, techniques like lamport timestamps and vector clocks maintain consistency across machines. Best practices for synchronization include minimizing critical sections, leveraging high-level concurrency utilities, avoiding over-synchronization, and testing regularly for race conditions and performance bottlenecks. To further enhance your understanding, explore advanced synchronization techniques, concurrent design patterns, and their real-world applications in areas like databases, cloud computing, and large-scale systems. Thanks for watching the video. Be sure to explore our channel for more content like this.